My name is Marcin Wnuk, and I will be talking today about reproducing kernel Banach spaces, or to be more concrete, how to obtain Cox-Maklowka inequality in the LP setting. This is joint work with Michael Gniebuch, Eike Hinrichs, and Alexander Lindenberger, and this is very much work in progress. So let us start. The main problem we're considering now is the numerical integration problem. That is, we would like to approximate the integral of some function f via a quadrature Q. And this quadrature evaluates f at points x1 up to xn and assigns weights c1 up to cn to those evaluations. To be able to perform a theoretical analysis of such an algorithm, we need to impose some conditions on input f. And what we do is we require that f comes from some fixed normed space of functions capital F. With that in mind, we are able to say what do we mean by a good quadrature. So we are able to define the error criterion. And in our case, this is just the worst case error. That is, we simply compare the integral with the outcome of the quadrature, take absolute value of this difference, and a supremum over all f's with norm 1. For the future reference, we will be always considering integrals over set x with respect to measure mu. And the space capital F, so the space from which our input comes, will be referred to as the input space. A very favorable class of input spaces are reproducing kernel Hilbert spaces. So let me just shortly recall what a reproducing kernel Hilbert space is. Well, a Hilbert space of functions H, such that all of those functions are defined on some set X, is called a reproducing kernel Hilbert space if it admits a reproducing kernel. And the reproducing kernel K is a function which goes from x times x into C, such that it satisfies two conditions. The first condition is that K, with the second argument fixed, is in H. And the second condition is that if we fixed any argument y as the second argument of k. So now we consider once again k as a function of the first argument. And now we take any function f from H, then the scalar product of f and this k seen as a function of the first argument gives us f of y. This is the reproducing property. Now it may be easily shown that if given Hilbert space H, such a function k exists, then it is unique. And this unique function is called the reproducing kernel of H. So why do we like reproducing kernel Hilbert spaces? We like them because we have a nice and explicit worst case error formula if input space is a reproducing kernel Hilbert space. And this is basically given here. So the absolute value of integral of f minus quadrature of f is upper bounded by a product of two things. One of those things is the norm of f, and the second thing is a function which may be described explicitly using k. So it's integral of k minus quadrature of k. I shall refer to this function as the representer. Now we know even more. In general, we have here the inequality, but there always exists an f for which this inequality becomes an equality. And in such a way, we immediately obtain the corollary, that is, the worst case error in a Hilbert space, in a reproducing kernel Hilbert space, is just given by the norm of the representer. All right. So reproducing kernel Hilbert spaces and Hilbert spaces in general are naturally associated with the L2 spaces. So the main question we are facing now is if in some situations, in some cases, you could extend similar Cox-Machtlavka type inequalities to the whole scale of LP spaces. And in my talk, I will give you one concrete example where it does work out. And this example is a scale of spaces induced by integral kernels. A little bit notation before we can go on. So P and Q are for me always exponents between 1 and infinity. And P prime is a conjugate exponent of P. That is 1 over P plus 1 over P prime is equal to 1. And similarly, Q prime is a conjugate exponent of Q. For a mapping F, we denote by R of F the range of F. Okay, and now we may go over to the main part of the presentation, so spaces induced by integral kernels. We start with two measure spaces, X and Y, and as the title already suggests, we would like to have some integral kernel. So for us, integral kernel is a function L which goes from X times Y into R, and we require that it has some regularity. We require, namely, that L with the first argument fixed is in LP of Y and in the LP prime of Y, which naturally forces it also to be in L2 of Y. Moreover, we are considering a mapping phi, which we assume to be injective. And this mapping takes an LP function J and sends it onto integral of J takes an LP function G and sends it onto an integral of G times L with the second argument, seen as a function as a second argument. Now, if you take a closer look at this formula, it is quite clear that phi of G is a function on X, and phi of G evaluated at point X is just the integral over Y, G of Y, integral kernel at point xy, and integrate it out with respect to y. So recall that we assumed phi to be injective, that is, no two LP functions on y yield the same function on x. With that in mind, we may define now our first protagonist, that is the space LP of L, which is simply the range of phi. That is, it consists of all the functions f from x to r such that there exists a function g in LP of y such that f is just phi of g. Moreover, since we have assumed that phi is injective, we may simply transport the norm from LP of y to our LP of L, which is seen by this formula. All right. So let us stop for a moment and think a little bit what happens in the case p equal to 2. And one can see quite easily that in that case, so L2 of L is just a reproducing kernel Hilbert space, and the reproducing kernel sends point xz to the integral of Lxy, Lzy with respect to y. Moreover, it may happen that L2 of L does not contain constant functions, and we may always append them by adding 1 to the reproducing kernel. All right. Now, I said in the beginning, we would like to have some kind of a Cox-Maklowka inequality for our LP spaces. And in fact, they are not that difficult to obtain. So for that, we need some additional regularity conditions on L. I will not go into the details. But supposing that we have those regularity conditions, then it is easy to see that the worst case error in the space LP of L has the following norm. So what happens here? First of all, we take a function which in a way resembles the representer. And the representer was I of k minus quadrature of k. Now we have I of L minus Q of L. And now we take the LP prime norm of this function. It turns out this may be easily transformed to the form which we know exactly from the Cox-Maklowka inequality. That is, we may indeed consider the representer, but now the norm is not the LP norm, but the LP prime norm, but the LP prime of L norm. Okay, so having said that, let us go over to a simple example. So in this example, we will consider X to be a non-empty set and Y to be some subset of the power set of X. So one may think, for example, about X being a unit cube in the dimensions and Y consisting of some geometric objects in this unit cube. So for example, Y may be the set of all circles or all subcubes, unchord subcubes, whatever. And for some historical reasons, we will denote this Y by B. Now, the integral kernel we are considering right now is of a very simple form. It takes a point X and a set from B, and it returns the characteristic function of B applied to point X. That is, it returns 1 if X is in B and 0 otherwise. With this, we may build up a reproducing kernel K. Okay, it stands here. And let us pause just for a moment to think about the interpretation of this reproducing kernel if nu is a probability measure. In that case, it works kind of in this way. We fix 2 points, x and z, and we draw a random set B according to measure nu. And now this reproducing kernel gives us the probability that x and z are at the same time in B. Okay, it's kind of a nice interpretation. Probably it will not be that important later on. So having defined x, having defined B, having defined L, we may define the space LP of L. So those are just all functions f from x into R, such that there exists a function g in LP of B, such that f is the integral of g times characteristic function. It is a well-known result that in such spaces, the worst-case error is some kind of a geometric LP discrepancy. And we would like also to recover this result with our theorem. And to do this, we need first to recall what a general geometric discrepancy is. So to this end, let us take a point set P consisting of points x1 up to xn. And let us first define the local discrepancy of this point set at some set B. Okay, with respect to measure mu and weights C. So this local discrepancy is just the measure of B minus the, in a way, empirical measure of B. What do I mean by empirical measure? This is measure supported at x1 up to xn, such that xi has weight ci. Okay, so this is the local discrepancy. And now in our setting, we may treat this local discrepancy as a function of B. And we may consider the LP norm of this function. And this way, we end up with the LP discrepancy or LP geometric discrepancy. Okay. Now it is an easy corollary that in the spaces just introduced before, the worst case error is just the P prime, LP prime geometric discrepancy. Why is it so? Well, let us recall the Cox-Machlavka. Cox-Machlavka said that the integration error, the worst case error, is just the norm of this quasi-representer, so to speak. Okay, now one easily sees that the integral of L is just the measure of B, and the quadrature of L gives just this empirical measure of B. So in this way, the integration error is indeed the LP prime geometric discrepancy. There are also many different examples of the LP of L setting, not only those spaces connected to geometric discrepancies. As some very typical example, let me mention the ANOVA univariate Sobolev spaces of fractional smoothness and also the anchored univariate Sobolev spaces of fractional smoothness. Nevertheless, this setting is somehow not rich enough to attack many well-known spaces of functions. That is, we have somehow to extend it. And our main motivation in extending this setting is that we would like to study the dependence of multivariate functions on different groups of variables, and we would also like to study the spaces of higher smoothness. And to this end, we introduce the small LQ capital LP spaces. I will refer to them later on just as LQ LP spaces. And the main idea here is that we consider a whole sequence of LP of L spaces, that is LP of L1, LP of L2, and so on. And the sequence is indexed by some set J. And for every such space, we have a positive weight gamma J. Now, on such a sequence space, we define the norm just by taking the small LQ norm of weighted norms in the LP spaces. Those norms in the LP spaces are weighted by 1 over gamma J. The problem is now somehow it's quite possible that every LP of Lj is defined on some different set, so consists of functions defined on some different set xj. And we would like somehow to bring all those functions onto a common set x. And to this end, we need also a sequence of surjective mappings, theta j, which go from this set x onto xj. And finally, we may define a function f just by summing up the sequence with appropriately changed arguments. So we just move the arguments from x to xj, so it makes sense to take fj of this argument. So I admit this is a very vague description. This can be made precise, but it would require a lot of time, and I don't want to go into the details now. I just wanted to say that the class of examples for this construction is very big, and in particular, it contains the weighted multivariate ANOVA Sobolev spaces and weighted multivariate anchored Sobolev spaces of different smoothnesses. So of smoothness 1, higher smoothness, but also fractional smoothness. Okay, so this is basically everything I wanted to talk today about. A few things about the ongoing work. So the first and the most important thing is taking a look at a different scale of functions. So function spaces which are not induced by integral kernel, and those are function spaces based on Fourier transforms, containing, for example, Harvey-Wavelets spaces or Walsh spaces. And then one would like somehow to connect them via embeddings to the spaces which were discussed just before. So thank you for your attention. And here are also some informations on the articles which were used when preparing this presentation.